Hello, this is your brain on drugs, and this is the punk rock psychiatrist. So I want to welcome you to a special, brief episode of This Is Your Brain on Drugs. Um, a couple episodes ago, I asked the question, why are mixed amphetamine salts a mixture of salts and not just a single salt? All of our other, and actually not all, I'm going to get to that, amphetamine products are salts or not salts that are base, and we're going to talk about what that is. But Adderall or mixed amphetamine salts, also including Mideas, are a mixture of amphetamine salts. You've got saccharate, aspartate, monohydrate, and sulfate. And the question is, why do we need the different salts? I actually had one listener write me and say that they thought it might have been a marketing ploy to differentiate it from the old dexedrine, dextroamphetamine products. And perhaps that may have something to do with it. But it kind of sparked my curiosity to actually see if I could figure out. I mean, why would they go to the trouble of making these different compounds and mixing them together? What is the purpose of this? And so I dug deep into chemistry to get you an answer. So for those of you out there that are chemistry nerds, you're going to get a little bit of what you're looking for. I try to do, I try to go into the pharmacology as deeply as possible in this podcast. That's one of the purposes of it. I mean, I freely admit I am not a chemistry major. I actually wish I were. I did really poorly in chemistry 2 in high school, and it kind of turned me off of science when I had been a big science guy. And I ended up taking like the easy route and becoming a business major because economics just seemed like an easier science for me to do. But I wish I had done more chemistry. And so there may be those of you out there that did more chemistry, and this is going to make a lot of sense to you. And maybe you knew this, but I've just discovered it and I'm going to report it to you all. So the question is, why a mix of amphetamine salts? All right, so let's kind of talk about what these different salts might do. I was under the kind of understanding that salts just dissolve in solution, and this sulfate or whatever it is that's connected to our active drug just kind of dissolves away. We don't really use it. And then the active drug is there and it's used. So why does it really matter? Well, let's find out. Um, this is, I thought to myself, are there any other medications that are a mixture of salts? And when you do I mean, I couldn't think of any. And so I did a Google search and it keeps trying to tell me that there are. But every single example it gave me were not mixtures of salts into one drug. There was the example of Xywav, which is about the closest that we can get. We haven't talked about that yet. That's a GHB, gamma hydrobutyrate product that is used as a awakening agent in narcolepsy. It's a newer product. We had Xyrem before, which is sodium oxybate. Xywav is a mixture of sodium, magnesium, potassium, and I think one other oxybate. And kind of the idea there was we're getting so much sodium with that oxybate product that we're kind of overloading the patient with sodium. They're already getting it in their diet. It's probably not good to have all this extra sodium. Some people are sensitive to it, could make their high blood pressure worse. So let's make a product that has lower sodium concentrations in it. And so in this case, they mixed the salts in order to lower the amount of sodium. Okay, that was like the purpose there. Let's make some different salts so that we don't have as much sodium. And that is the only other mixed salt that I can find. If you know any, let me know. There are several products that come in a variety of salts. I'm thinking of hydroxyzine, hydrochloride, but then you've got hydroxyzine pamoate. So you've got different products, but it's not a mixture of salts. You have a choice between two different salts. And then sometimes a generic product might be a different salt than it's a patented brand name product might use a different salt. And the FDA says basically, well, the active drug is the same, so we don't care what salt you made it into. it's still equivalent. Um, and so there are products like that. But what's interesting about mixed amphetamine salts is it is really the only product I can find other than Xywav that's a mixture of salts, but it's unique in the reason why I think that they're doing it. All right. So let's dig into why, right? So the effect of different salts is different with different pHs. All right. So this is the important thing that you have to note. There are neutral salts, basic salts, and acidic salts. A neutral salt is formed from a strong acid, strong base combination. Think of table salt, sodium chloride. So this is a formation of a strong acid base combination. And these are neutral and they are mostly not affected by pH. So the pH of whatever solution you dissolve salt in, or table salt, sodium chloride, it's going to dissolve pretty much the same. All right. But that's not the case with basic salts and acidic salts. So a basic salt is formed when you have a weak acid and a strong base, and they are more soluble in acidic solutions. Now we have acidic salts, which is what mixed amphetamine salts are. Acidic salts that are formed from a strong acid and a weak base. Amphetamine is a weak base. Okay. Its pKa is 9.9, so it's a weak base. 7 being neutral, getting up to 14 would be like more strongly basic. So 9.9 weak base. These acidic salts are more soluble in basic solutions, such as when you advance down the GI tract. And we're going to talk about what the pH is at different points in the GI tract here in a second. So think about this. So these amphetamine salts are more soluble in basic solutions. However, each salt of amphetamines dissolves better at different pHs because it depends, you've got the weak base. So remember, acidic salt is formed by a strong acid and a weak base. But strong acids could be different pH, strong 1, 2, 3 pH. Those are all strong, but one is stronger than another. And so you're going to have a variety of different acidities of the salt formed by amphetamines. Okay. And that's where I think this is where the mixed amphetamine salts story gets interesting. All right. So in the stomach, it's very acidic, right? So amphetamine salts become more ionized and less absorbed. This is the other concept to understand. You have amphetamine as a base, just plain old amphetamine. It is lipophilic, meaning that it is more soluble in fat. And if you see amphetamine base, it tends to be oily residues. All right. I, ionized amphetamine is more hydrophilic, right? So this is the salt form. What's happened is there is an extra H or hydrogen added to the amphetamine molecule. And so it's an amphetamine with a positive on the nitrogen and an extra hydrogen that is bringing that positive charge there. And then that gets mixed with a negative ion such as sulfate, right? SO4, what is it? 2 minus, something like that, right? But the point is it's an anion, and amphetamine is a cation or positively charged. Okay, so in the stomach, because it's a low pH, amphetamine, which is an acidic salt, weak base combined with strong acid, is going to be more in its salt form, which is it's going to be more ionized and then less absorbable. This is the other point. In the lipophilic form, it's more easily absorbed through the GI wall. All right. So in the intestines, if you have a lipophilic substance, it's absorbed more easily through the GI wall. And so if we're in that ionized form of amphetamine, it's not going to get absorbed. But as the pH goes up, it changes into that base form, the lipophilic form, and gets absorbed into the intestines. Okay, that's the cool part. All right, so Lipid-soluble forms of a drug like amphetamine base are absorbed better in the GI tract, and water-soluble forms of a drug like amphetamine salt dissolve better in the GI tract. All right. So this is another important point. So this is pretty complicated. It took me several hours to solve this problem. Um, so when it's in its ionized form, it is more water soluble and it dissolves better in liquid. Okay. And we need the drug to dissolve in liquid so that it breaks up into tiny little pieces that can all individually be absorbed. If you have the base form of amphetamine, which is lipophilic, and it does not become water soluble, it stays in this big oily chunk. And that big old oily chunk cannot be absorbed through the intestines. It has to become water soluble to break it up into tiny pieces. Then it has to be switched to its lipid soluble form, its base form, to be absorbed through the wall. So you need a combination of a hydrophilic amphetamine to dissolve that changes to its base form at the right pH for it to absorb in the GI tract, right? So it goes into the stomach, acidic environment, it becomes it turns into it's in its ionized form. pH rises as we leave the stomach. Once we get to the correct pH for that particular salt, it's going to switch into its base form, lose the sulfate or saccharate or whatever is attached to it, and get absorbed through the GI tract. Does that make sense? All right. So let's talk about, and this was a little hard for me to find. Um, Different salts dissolve differently depending on the pH of the solution if the salt ions are the conjugate acid base of a weak species. All right, which is what amphetamine is. It's a weak species of base. And so amphetamine sulfate is going to dissolve at 5.0 to 6.0 pH. Amphetamine aspartate monohydrate, I just found less than 6.0. I wasn't able to get exact numbers on that one. And then amphetamine saccharate, it just said 1.2, but it also kind of referred to saccharate like the other salts. So it's unclear to me whether it's saying that saccharate specifically was 1.2 versus they're all like that. It said at 1.2, and then it becomes less soluble as the pH increases. I think the exact numbers here are less important, but the important thing is the pH at which each of these three salts dissolves is not the same pH. All right. And then the pH throughout the GI tract changes. Mouth and esophagus, we're at 6.5 to 7.5 pH. At the stomach, if we're fasting, 1.5 to 3.5. After a meal, it goes up to 3 to 7. So this is why some drugs it will say take with food, right? Because taking it with food increases pH, and that may assist with that particular medication in being absorbed. So if you take it on an empty stomach versus you ate something, you affect the pH of the stomach and you affect its absorption. Some drugs are going to be unaffected by this. 50% of drugs are salts and 50% aren't, right? So it depends, are you a salt or are you not a salt? And what pHs is this salt going to dissolve at versus a different one? And what's the pH that we have at the time in the stomach, depending on whether we ate or not. And so, I don't know, to me, this is super cool because it means this explains why different people at different times with different meals are going to have different experiences with the drug working. And this is, I mean, this is super important to know. And like, this is something I was never taught, I learned today. All right. Once we get into the duodenum, which is the beginning of our small intestine, our pH is dropped to around 6.0. When we get to the jejunum and the ileum, which is the distal part of the small intestine, we're up to 7.0 to 7.5. When we move into the colon, the large intestine, our pH drops again, 5.5 to 7.0. It will drop to around 5.5 and then increase to 7.0 as it moves through the colon. And this is due, this decrease, you may be wondering why, like, well, we're starting at a low pH because we're in the stomach and there's acid in the stomach. And as we move further away from the stomach, we're further away from the acid. but then the colon goes back down again. This is due to bacterial fermentation. So bacterial fermentation going on in the colon has an effect of lowering the pH. All right, so as you can see, the pH changes as we move throughout the GI tract. And so when I'm thinking what's going on here with these different salts is that each of the salts is absorbed at a different point in time, depending on what the pH is, because they're all going to be in the same location because you take the pill at the same time. But at that location, we might have a 5.0 pH at this time, and then a 5.5, and then a 6. And like each of those salts is going to change into its base form at a different point in time, right? They're going to start out ionized and they're going to change into their base form as the pH goes up. And that's going to be a different point for each one of those different salts, which means that they're going to be absorbed at different times, some sooner, some later. And what I imagine the idea here is that we're getting a smoother transition of the medication into the bloodstream and activated in the brain. All right. So if one of the salts gets absorbed more quickly, say the saccharate form, that it's going to deliver amphetamine a little bit sooner, and then say the aspartate comes next. I'm not sure if aspartate or sulfate comes next because one says less than 6 and one said 5 to 6. So I'm going to guess it's aspartate, and then the amphetamine tied to aspartate is going to come in later, and then so the one attached to sulfate is going to come in last. And so we have kind of a more continuous even flow. And that's what we've been talking about in these episodes. The drugs that have more even curves rather than spikes work better. And the spikes are like the medication all comes in at the same time, all gets released at the same time. So I think what these salts are doing are smoothing those curves out because of this different dissolution and reconstitution into base form with different pHs with different salts. All right. So now we have a flip side on this. All right. What happens when the drug leaves the body? Right. So the acidity of urine is going to affect the excretion of amphetamine. Acidic urine decreases the half-life because more amphetamine is in the salt or hydrophilic form, right? Because remember, in an acidic environment, we're more in the hydrophilic form. And then when we have a drug in the hydrophilic form in our renal tubules, they are not easily reabsorbed back into the blood. And therefore, we'll get rid of the compound more quickly, and that will lower its half-life. If we have a more basic urine, so now we're more in the base or lipophilic form of the amphetamine, it is going to be reabsorbed from the renal tubules into the bloodstream more easily, which will extend the half-life. All right, so the acidity of the urine is going to affect how long the drug acts, and the acidity of the GI tract is going to determine when it gets absorbed into the blood from the GI tract. So how soon it's going to kick in, right? So it's the same concept of pH here, but like we're talking about absorption versus excretion, all right? And you may be wondering about the acidity of the urine. Sometimes your urine varies in its acidity, and certain foods and also certain medications that you eat can make your urine more acidic or more basic or more alkaline, which is basic, right? What foods make it more acidic? A lot. Meat, eggs, rice, pasta, bread, cereals, prunes, plums, cranberries, corn, white beans, lentils, yogurt, buttermilk, cola, coffee, alcoholic beverages, and ascorbic acid, which is vitamin C. Remember when I said before, if you're trying to get to sleep and your drug is still active and you want to get it out of your system, I think I said 2,000 milligrams, or was it 1,000 milligrams of vitamin C? This is why. When you take that vitamin C, it's going to acidify your urine. It's going to decrease the half-life of your amphetamine, and it's going to get kicked out. Now, you could also do that. So, those of you out there that are drinkers and you're wondering why your amphetamine is not working as long as you would like, well, that alcohol is acidifying your urine. If you're a cola drinker or a coffee drinker, that could be acidifying your urine and getting rid of your amphetamine sooner. And so if you want to extend the life of your amphetamine because it's not lasting long enough, avoid eating these foods. I mean, there's a lot of foods in there, but like avoid as many of them as you can. Um, Contrary to that, there's foods that make your urine more alkaline. Apples, bananas, cherries, melons, broccoli, beets, leafy greens, potatoes, legumes, nuts, seeds, herbal teas, mineral water, and citrus fruits. And then you may be wondering, citrus fruits, aren't those acidic? There's other acidic items like cola that made my urine more acidic. Why? And ascorbic acid is acidic. Wouldn't that make my urine more acidic? Why are citrus fruits, which are citric acid, not making my urine more acidic? They're making it more alkaline. Well, citric acid is actually converted into bicarbonate in the body, so it ends up getting turned into a alkaline agent, even though it enters the body acidic. So a little that's a little twist to the story. So if you have citrus fruits, it actually will extend the life. And you may be thinking, oh, grapefruit juice, does that, but that's through it's an enzyme activity. It inhibits 3A4. But grapefruit juice will also alkalize your urine, which can affect some medications. Now, not all medications are affected by this. Amphetamines happen to be. However, if you'll note before, I said that lisdexamphetamine lisdexamphetamine is not really affected by this, and that has to do with how it's activated after it's absorbed into the body. All right, so less affected. Um, Amphetamine, and then I think that also points us towards what about the amphetamine-based medications? Now, I made a mistake before, and I said that the base medications were Dianavel, Adzenys, and Evakeo, because that's what they were listed when I looked them up. But what I found out is these are actually not base medications. They're listed in a category called single ingredient medication. So I remember when I was talking about Evakeo, I said, well, this is amphetamine sulfate. That's a salt. Why does it say it's base? I was confused. It's not base. It is a salt, but it's a single ingredient. It's a 50-50 mixture of dextro and levo amphetamine sulfate. So it's a single ingredient. For whatever reason, they group it into the single ingredient category. Adzenys is also single ingredient, but it is actually base. So it is, and so you might be wondering, well, if it's base, then doesn't it have to become like ionized so that it gets broken up? Well, if you remember how Adzenys is formulated, it's a liquid, and it's was it a chewable or I think oral disintegrating tablet. So it's already broken up into its component parts in the medication. So it's not clumped. It's already dissolved in liquid or an ODT. It's already dissolved. And so we don't need to worry about dissolving it further. And so it can just go straight through in its base form and get absorbed into the GI tract. Another base medication, there's only two, is Zelstra, which is a dextroamphetamine product, and it's absorbed through the skin. So once again, we don't run into this need to have it dissolved in order to get it absorbed because it doesn't go through the GI tract. Those are our two amphetamine-based medications, Zelstra and Adzenys. All right. Dianavel, which is another interesting story. Not only is it not a base medication, it's not even single ingredient. And remember, I had kind of a question mark of what's in there. It's 3.2 to 1, so it must be a mix. So how is it single ingredient? How is it, how is it a base? I didn't really understand. I now found out. Dianavel is listed in the single ingredient category, even though it isn't. And it's also not a base. So this is the quote I found. The FDA decided to express Dianavel XR's strength and established name in terms of the amphetamine base equivalent to prevent confusion with other mixed salt products and reflect that it is essentially a single drug product. Well, guess what? Adderall is also a single drug product. It's amphetamine. And they say, oh, well, it's a mixture of levo and dextro. Well, so is Dianavel. So for whatever reason, they decided to categorize Dianavel differently. But you know what? Dianavel is a mixed amphetamine salt. It is in truth, but in reality of how the FDA is categorized, it is not. And you may be wondering, so it's a 3.2 to 1 racemic mix of dextro to levoamphetamine. What is it made out of? It is a mixed salt of dextrolevoamphetamine complex with sodium polystyrene sulfonate. So that's the salt. That's the first salt, and that is an ion exchange resin to provide its extended release capability. And then there's dextroamphetamine sulfate in there, and there's a dextro-levo racemic amphetamine mix aspartate in there. And so, yeah, it is a mixed amphetamine salt. But if you look up mixed amphetamine salts, you will only see Adderall, Adderall XR, and Mydayis. You will not see Dianavel. You will see it under a single ingredient. I think that's weird that we've decided to categorize it with a different definition, even though it meets the old definition. And so those are some points that I was kind of confused when I was going through that talk. And now we understand Evakeo is a salt. We understand Dianavel is a mixed amphetamine salt, but it's not. And we understand why foods affect amphetamines. We're going to talk more about what foods affecting amphetamine and how we can use that to our advantage or disadvantage. But you're probably, gears are going now and you're thinking, oh, these foods will make it last longer and these foods will make it last shorter, right? Due to the acidification of the urine. And now we understand why having multiple salts in one medication might make it better. You know, we're always looking, and when we're talking about these stimulants, we're always looking for medications to have the smoothest curve possible. Zelstra has a really smooth curve because of its patch formulation. It's slowly absorbed from the patch and through the skin. Lisdexamphetamine 5-ance has a smoother curve because of the way the enzymes in the red blood cells cleave it in a slow manner. And we're gonna meet more of these categories. And Dianavel, it has the smooth curve because remember, it's got the little polymers on or surrounding, was it polymers or some sort of substance surrounding the drug of an infinite number of thicknesses. And so as we're eating through that substance to get to the drug in the middle, we have all these different thicknesses. So it's going to take us longer for some than others, and it's going to be a very continuous pattern. And so that gives us a smoother transition. And now for the mixed amphetamine salts, we see that they may have their more smooth transition because of the different salts used. How much of a difference is this going to make? I don't know. But I always wanted to know why we have to mix salts. And, the answer was not just interesting to me, it also explained to me why different salts are used in different drugs. I mean, we don't necessarily have to have mixed salts, but using different salts is going to affect a drug differently than another one. And one salt of a drug versus a different salt of a drug may give a different effect, and this explains it. And then this whole acidification of the urine thing, that also helped me understand how excretion works in general. And so asking, and so some people, I think they might say who cares? It's a mixed amphetamine salt. I don't even need to know what kind of salts it is. I don't even need to know that it's a mixed amphetamine salt. It's Adderall. I know that it's called Adderall. I know what Adderall does. I give Adderall to my patients, and then I set it and I forget it, right? Well, those of you listening to this podcast do not think like that. And I think when we ask questions that might seem like who really cares, we might end up finding out answers where we learn things that actually are really useful. And I think the answer to this question was useful in 10 different ways. And I hope you are as excited to hear those different ways as I was to learn about them. And so we had a shorter 30-minute episode today where we answered this interesting question that I asked before. Somebody threw me an answer. I looked it up to just kind of see are they right? Is this why? I need to figure this out for myself. And so I spent all day on this because I'm a pharmacology nerd. I should have been a chemistry major. And I'm a wannabe chemistry major, with all the nutrition stuff. I'm a wannabe nutrition scientist as well. I try my best. I know I'm not any of those things, but people like you and me that prescribe these meds, we're the ones at the end of the line having that effect on the patient. It's not the scientist. And I find it interesting when we look at when I try to find out why what sent me down this whole rabbit hole of what I do in this podcast, where I explain how one drug is different than another drug and why I wondered why one drug is different than another drug. I wanted to know how tiny differences in the chemistry of how these drugs worked impacted what effect it could have with the patient. And so when people are having different reactions to medications, I wanted explanations for that. And I wanted to be able to dive deep and see if, maybe the reason why they weren't tolerating this was because of some factor, like they're having too many oranges, something like that. Like, I think knowing this stuff, it gives us this information on how to treat our patients more effectively. And it's like, it's not the scientist isn't that created these drugs is not giving them to the patients, and when I wanted to know kind of when I wanted to find out how are these drugs different, what source did I go to? I went to the drug companies, you know, like advertise to me. Tell me why your drug is better than another drug. I mean, isn't that what these drug reps do? Isn't this what their information sheets should be doing when I go on their website? And what I'm kind of disappointed to find out is I go on their website and they don't really explain to me what sets their drug apart from other drugs that are in similar categories. They just say, oh, this is another option. Sometimes they might say this lasts longer or it's better tolerated by patients. But they don't give they're not really giving me the scientific answer. And I know whoever created these drugs knows why they made the mixed salts. But then when you go to look it up and you go on the websites of Adderall or the company, they don't explain it to you. They don't say, hey, our product is good because we do this, and this is why. And I don't understand why you wouldn't want to explain that. You know, people don't have to read it if they don't want to. I mean, I know they're trying to make it easy to understand for like people taking the medication, but have some fine print. Have those details. When I look through your drug information sheet, you don't talk about this. Why? Why do I have to dig and dig and dig and ask all these different questions to try and ferret out the answer? Because this could actually explain why your product is the one that I should use with the patient in front of me. Do they want to confuse me? Do they want me to just be attached to the name and the commercial and the ad, but not have the real knowledge? Perhaps if if they think that we have the details of how all these drugs are different from one another, we won't prescribe their med as much. Perhaps that's what it is. Perhaps they'll think, oh, well, then we'll explain what niche patient this might work in, and then they'll only use our drug in that niche patient, and they won't use it in other patients. They'll use these other drugs that work better with those niche patients. And so perhaps they want to keep us in the dark. I mean, you have to imagine that it's intentional, that they don't really want us to know all this information because they don't want us to personalize medicine. They don't want us to be able to figure out the best med for the best patient, because then you know what's going to happen. We're going to prescribe a wide variety of medications, and they want us just to use theirs. They want us to associate their drug with working. They don't care if we understand what makes it different or what makes it better. They'll show us a chart that says, look, it's better tolerated, but they don't explain why. Because if we knew why, then we would know exactly who to give it to. And we would know not to give it to some patients, and they don't want us not to give it to some patients. All right. That's my guess. Because these companies, their whole aim is to make money. And mine is to make patients better. And I think a lot of people might say, well, it really doesn't matter which one you give them, or just give them one. And then if it doesn't work, try something else. And it's like, wouldn't you rather get it right the first time? And then if the reason why the medication didn't work is because of something the patient did and not because it might be how they took the medication, whether it was with food or without, or at the wrong time of day, or with another medication, or with a particular type of food or something. And that's the reason why it's not working. And we can just give them the information of, hey, do it this way, but this drug is still like a good option for you, rather than switching to something else that might not work. We could use the one that actually is working, but they're just not taking it right. Well, that's the aim of this podcast for me. It's for me to personally learn how all this stuff works and communicate it to you so that you can better get your patients better faster, because the drug companies, they don't really care about that. The patients care about that more than anyone. And then I care about it. I mean, I care about it almost as much as the patient does. I get such a dopamine high when I hit something out of the park. I mean, I can't tell you how many patients I've been more excited that they got better than they did, because a lot of the patients are just expecting to get better. Oh, I see a doctor. They give me a med. It's going to work. They know what they're doing. And, we don't always know what's going to work best. In fact, in psychiatry, we rarely know what's going to work best. So when I feel like I got somebody better faster than I expected, I get super excited. And I think they think it's funny. It's like, why is this guy excited? I'm supposed to get better, right? Like, isn't that how this works? Well, sorry, patient. Psychiatry is kind of a crapshoot. Um, and it's really hard to know what works. And for me, understanding the chemistry is what helps me get there. And hopefully that's what you like as well. And I hope you enjoyed this really interesting, detailed discussion on mixed amphetamine salts. And I hope you'll join me on the next regularly scheduled episode. Thanks for joining me.